Industrial manufacturing operates on a scale of massive forces and continuous motion. Every rotation of a gear, every stroke of a press, introduces microscopic wear to the physical structure of the machinery. Historically, facilities managed this wear through calendar-based maintenance schedules. Technicians replace parts based on rigid time intervals, an approach that either wastes perfectly functional components or fails to intercept sudden, catastrophic breakdowns. To solve this inefficiency, industrial systems are shifting to condition-based monitoring, or CBM. CBM continuously or periodically tracks measurable physical signals emitted by the equipment. By capturing this data, engineers accurately infer the current health state and degradation trajectory of a specific component. This stream of condition indicators functions as the core data engine powering modern predictive maintenance workflows. The ultimate target metric for maintenance planners relying on this data is RUL, or remaining useful life, a strict calculation of exactly how much operating time a component has left before failure. Calculating an accurate remaining useful life trajectory from raw, chaotic physical signals remains the most complex, time-consuming bottleneck in predictive maintenance. Solving it requires a highly specific, multi-layered technical architecture. The bedrock of that architecture begins at the machine level, tracking the physical energy the component emits as it operates. Vibration monitoring is the dominant modality used for rotating equipment. Accelerometers capture the raw kinetic motion of the machine. This animation illustrates how dynamic signatures of imbalance or bearing defects are isolated. By extracting specific time domain and frequency domain features from the accelerometer signal, distinct mechanical fault types become mathematically visible. For motors and power electronics, temperature monitoring is essential. Regression-based predictors track thermal trends to provide warnings of hotspot development and thermal runaway before severe physical deformation occurs. Acoustic and vibroacoustic sensing capture complementary, low-magnitude signatures. These high-frequency audio profiles detect early-stage mechanical damage when the fault is still microscopic. In process industries and manufacturing lines, process variables like pressure, flow, and force provide critical operational context, offering longer warning periods for die and tooling damage than vibration metrics alone. Engineers apply statistical regression models and machine learning classifiers to these individual data streams to map out degradation trajectories over time. Capturing individual modalities maps isolated physical phenomena. Relying strictly on a single signal type to predict equipment failure creates significant blind spots for predictive models. In early predictive deployments, a major structural risk is the frequency and high operational cost of false positive alarms. A single modality, such as a solitary spike in vibration data, easily triggers an erroneous alarm due to overlapping environmental noise or a temporary shift in operational load. Multimodal fusion resolves this ambiguity by integrating multiple sensor types into a cohesive analytical model. This chart tracks 3 distinct data streams: vibration, acoustic, and temperature. By cross-referencing process variables against physical signals, the system identifies a synchronized anomaly across multiple modalities to mathematically confirm a true mechanical fault. This fusion mechanism filters out isolated noise and strictly reduces false alarm rates in live industrial deployments. Combining these modalities also improves early-stage detection sensitivity, pinpointing the earliest microvariances of degradation long before a single sensor registers a problem. While multimodal fusion provides high diagnostic clarity, it creates a severe data throughput problem. Generating continuous, high-frequency raw data from multiple sensors rapidly overwhelms standard industrial networks. Sending raw, uncompressed vibration and acoustic waveforms from hundreds of factory sensors directly to centralized cloud servers is mathematically unscalable. To eliminate this bandwidth bottleneck, engineers move the initial data processing out of the cloud and relocate it directly onto the physical casing of the machine. The hardware facilitating this includes triaxial accelerometers and low-cost, ruggedized MEMS units, such as the ADXL series sensors. Integrated inside these compact units are embedded microcontrollers, primarily utilizing the ESP32 platform, which act as the localized brain of the system. These microcontrollers host TinyML algorithms, highly compact machine learning models designed to run locally on low-power devices. The TinyML classifier ingests the dense, fused analog data directly from the sensors the exact millisecond it is generated. This localized processing architecture executes with extreme speed, completing vibration-based fault detection with sub-100 millisecond latencies. Instead of transmitting megabytes of continuous waveform data, the edge node distills the physical noise into a lightweight binary output, the actual inference of the machine's health. Edge classification identifies exact mechanical fault types immediately, bypassing the need for remote centralized servers to decode raw vibration patterns. By translating gigabytes of physical analog noise into kilobytes of actionable digital insights locally, edge machine learning converts a crippling data transmission problem into a highly scalable architectural asset. Zooming out from a single isolated sensor node, a typical manufacturing facility requires tracking hundreds of automated assets simultaneously. To connect these distributed edge platforms across expansive square footage, facilities deploy an Industrial Internet of Things, or IIoT, architecture. Local gateway nodes aggregate the health inferences generated by the edge sensors, cleanly integrating legacy machine tools into the modern network. The transmission protocols driving this rely on low-power wide-area networks, specifically LoRaWAN, operating alongside 5G backhauls. Because the intense computational work of processing waveforms is already completed at the edge, facilities utilize LPWAN protocols to transmit the lightweight data. This keeps overall hardware costs and power budgets exceptionally low. This specific distribution of labor and transmission allows the IIoT network to seamlessly scale to thousands of individual sensor nodes without network congestion. The gateway routes these consolidated inferences through the final leg of the journey, delivering them into centralized, cloud-based analytics dashboards. This vast IIoT topology functions precisely because the computational heavy lifting is systematically distributed to the edge rather than forced into the cloud. Reviewing the complete predictive maintenance pipeline reveals a logical progression from physical mechanics to digital strategy. In Phase 1, physical degradation is captured via continuous, multimodal sensor tracking at the source. In Phase 2, that dense data is classified locally in milliseconds using TinyML on embedded microcontrollers. In Phase 3, this low-bandwidth inference is transmitted wirelessly to the cloud. This end-to-end architecture ultimately delivers the specific maintenance teams require: accurate, real-time remaining useful life predictions. Maintenance planners read these centralized dashboards to execute precise, condition-driven interventions, ordering parts and scheduling downtime exactly when the data dictates it. This approach bypasses raw data overload entirely and eliminates the inefficiency of reactive calendar schedules. This specific architecture of physical sensors, localized intelligence, and network topology provides the framework necessary to systematically decode industrial signals and achieve true equipment prognostics.